Hello, this is Jim Corkins, and we are continuing moving on through energy. We are in 3.2, and what we're going to talk about today is the rest of the type of energies. And also, so if you haven't read the Coletta textbook, please go to Chapter 7 and finish reading it up. Again, we are continuing with energy, homework number 9 for Physics 111. Physics 112, we're doing homework 6 in energy. And we'll be finishing up lab number 9 in this PowerPoint too. So, this is some random knowledge that I came across in the internet. I thought it would be kind of funny to put it in here. Apparently, there was a really cool article that was published that these scientists taught rats how to drive in these little itty-bitty carts. And apparently they love it, and they actually feel very relaxed when they're doing that. Well, one thing led to another, and I kept researching random knowledge about cute little rats. And I found out that rats actually do laugh and giggle when they are being tickled. So I put links to both of these articles here in the PowerPoint, in the PDF. If you want to click on it and just check it out, it'll make your day a lot better. I guarantee it. And I actually love the fact that rats will giggle at ultrasonic sounds, and they will actually seek out being tickled. So anyways. Moving on, here we go. So far we've gone through the basic energy model, how work transfers between energy systems, and then also heat as well. And we've also learned what a system is. So you define a system by the interaction of objects, and that if there's any type of energy that leaves that system, it leaves that system forever, or enters that system, it will increase the amount of energy in that system. We've also learned that there is such a thing called the conservation of energy, the law of conservation of energy, and that when you sum up the differences of all the different types of energies, that is equal to 0. And we also earlier we had talked about the work energy equation. And that's actually when you sum up all the differences of energies, that is equal to the amount of work that is left over, that has left the system or is being brought into the system. Okay? So we're going to be talking about, one last thing. Typically when you have energy leaving, when you have work and heat entering or leaving a system, that is called a non-conservative energy or non-conservative force, right? When all of the energy, when you sum up all the energy and there is no difference, meaning the energy in is equal to the energy out, then that is called conserved energy, and all the energy is retained in the system. But when the energy in is not equal to the energy out, that difference in energy is the amount of energy lost or gained to that system. So that comes from the outside, and those are called non-conservative. That's a non-conservative energy or work. Okay? So what we're going to do, we've been concentrating on what kinetic energy is, potential energy due to gravity. And we only talked about potential energy due to a spring and heat and chemical energy. So now we're going to get into that. And actually, we're not going to get into chemical energy. We're going to talk about spring, potential energy due to a spring, and how do you get heat into a system and out of a system, right? And usually that's through friction, right? So static friction, kinetic friction can add or take out of a system. So let's begin, and we're going to begin by reviewing everything. So there are all different types of forms of energy. The mechanical energies are kinetic energy and our two potential energies. We have a gravitational potential energy. We have a spring potential energy. But there's this other type of energy, which is a non-conservative energy, which is energy that's entering a system or leaving a system, and that's thermal energy. There's a couple other types, chemical energy and nuclear energy, and we kind of went through what those are in 3.1 and how, and also a little bit about energy transfers. So these are all the mechanical energies, okay? So we have kinetic energy is equal to 1/2 mv squared. There's another type of kinetic energy called rotational kinetic energy. And when we get into rotational motion, centripetal acceleration, rotational motion, basically stuff going in a circle, we are going to talk a lot about this. But we're not going to worry about rotational kinetic energy in energy right now. So potential energy due to gravity is another type of mechanical energy. It's mg delta y, right? Delta y because it's moving up and down. That's the y-axis. Spring energy comes about, and I'll go ahead and mark this document up right now. Plug that back. I'm going to go ahead and do this. So potential energy due to a spring comes about by integrating the spring force Kx from the initial to final, right? And when you do that, you get 1/2 Kx squared from xi to xf. And what that becomes is k delta x squared, right? After you put in your limits and subtract them from each other, that x becomes a delta x, right? And if you recall that k here is the spring constant, and that delta x is how far the spring has been stretched or compressed past the equilibrium position. Stretch or compressed. Okay, so that's the other form of mechanical energy that is a potential energy. So it's springy. And this applies to springs, rubber bands, anything that's stretchy or compressy, right? Sponges, for example. Okay. And the reason why that is a potential energy is because once you compress it or stretch it, that energy, that the work that you just did gets stored in the spring system, right? So that's, since we're calling it a stored energy, that is technically a potential energy. Okay. So basically, here is a really great slide where this is all the types of energies that we are going to be using in this unit, right? Just laid out in equation form. And I've kind of made a little notations that if you have kinetic energy, that means the object is in motion, okay? If you have any type of potential energy due to gravity, that means the object has a height, right? And here's the equation. If you have a spring energy, well, if the object is touching a spring, well, this is the potential energy due to a spring, and that's 1/2 the spring constant times the deviation from the equilibrium position squared. And then there are the non-conservative work systems, right? These are the two guys that can add energy to a system or take energy away, right? It's basically the energy exchange system. These guys are what are being exchanged between the mechanical energies, right? So again, this is the work energy theorem. It's work equals force times a displacement. And we talked about how the force vector has to be parallel to the displacement vector, and actually there's probably a cosine of theta along with this, right? And we also have, but now we have this heat stuff, right? We have heat. And that actually comes from friction, right? So when an object heats up, you got to ask yourself, did you put it on when you slide a block across the floor, and we're going to be we're not going to be dealing with boiling water or any of that. That's more like if you would do like chemistry kind of stuff. But if you have a block sliding to a stop across rough ground, well, that kinetic energy, that kinetic energy is work, so that kinetic energy is going to be negative now. So the friction is going to be doing negative work on the block, which is going to be taking kinetic energy out of the block, right? And so this work due to friction, sometimes it could, in a few instances, it can add energy to a system, right? But most of the time, we're talking about frictional energy taking work out of the system. Basically, taking kinetic energy, converting it, taking kinetic energy out of the system through friction, converting it in the heat into heat, which then gets bled out of the system. Okay? And when we apply the pie charts and the energy bar charts in the next couple exercises, when we go through each one of these, what we're going to try to do is we're going to actually keep that internal energy in the system and account for it as part of the system, right? And then if we choose, we could actually say that leaves the system. You'll see when we get to it. All right? So moving on, let's just readdress what work is, right? Work is a force times a displacement vector, right? So this weightlifter is doing, it looks like he's doing a snatch. It's a weightlifting move. So he's lifted a barbell, and he's applied a force which has lifted a barbell, mg, upwards, right? And just to keep things simple, we're going to say he moves it at a constant velocity, and that is making it displace upwards, right? Well, that displacement vector is now in the same direction as the force vector, so this is going to be positive work, right? Just to remind you. Okay. If he was pushing on the object but it was moving down, if he was pushing up on the object, so if his force is opposite the direction of the displacement, that's going to be negative work, right? We kind of talked about that, which is going to result in like a negative kinetic energy or something like that, right? So in this case, he's doing positive work, and the work he's doing is actually the weight of the object, right? So we've talked about that, and we have a bunch of examples. And again, just to remind you that energy and work are both in the unit of a joule, and a joule is a Newton times a meter. It's a force times a distance, right? Force times a displacement. Cool? Well, let's do an example, right? Let's do an example using energy bar charts and pie charts and create an equation using work, okay? So here we go. We have a guy who's holding a weight right here, and initially this weight is not moving, and he brings it up. He lifts this up, or she lifts this up to a height. So it was initially a height h sub 0 off the ground, and now they're going to lift it to the air a height hf, okay, and bring it to a stop. So let's do some pie charts, right? And what helps me doing pie charts is listing off the types of energies that I'll be working with, right? So right in this area, I left it blank so you could utilize it. So, mgh. So they're the different types of energies due to a spring, which is going to be 1/2 k, 1/2 the spring constant times the distance, the stretch or distance squared. We also have internal energy, which is friction, which is the friction force times a distance, so times a displacement, right? So delta R. And also, as always, we have the work done is a force times a displacement as well. Okay, delta R, delta D. This is a displacement too. And H is a displacement too. But we're going to just keep it simple. Here's our basic stuff. Kinetic energy, if it's moving, if it's got a velocity, this is if it's got a height. This is the velocity if it's got a height. This is if it's got a spring. I'll put a little squiggly mark for a spring. This is if friction is working on it, so the terms rough ground is going to be there. And this is if a hand or a rope, so work, this, I only use this as if a hand or a rope or something, an outside force is touching the object. So here we go. So this weightlifter person is holding the mass here in his hands, or her hands rather, and the object isn't moving. Then what she's going to do is drive it up into the air and hold it there, okay? So what I want you to do right now is, given that description, I want you to try to attempt the initial energy and final energy pie charts, and also do the bar charts. We'll then pause, I'll talk to you about it, and then we'll correct any issues. And then what we're going to do is then do another thing where I want you to write out the equations of the corrected version, and then we'll talk about it again. And that'll be the format that we're going to do when we go through these different problems. So go ahead and pause the video and do the pie charts and bar charts now, okay? All right, well, here we go. We have a person, basically, let's take care of these stuff. You have a mass, a height off the ground, and anything that has a height off the ground is going to have a potential energy, okay? So it's going to have a potential energy initial, okay? And let's actually, now that we're talking about potential energy due to gravity, let's talk about here at the end. Initially, it's not moving. It's a height off the ground. There's no springs. There's no friction. There is a hand touching it, but we need to talk about that for a second. In the end, the pie, it's off the ground as well, okay? So it's got a potential energy in the end. It's not moving. It doesn't have a spring, or there's no rough ground or rough surface taking, converting friction, kinetic energy to friction, and then to heat. But let's talk about the work part, right? So initially, this thing is only let's just say this, it's only 1 block off the ground, right? But it's going to get to a height of h sub f. How is it going to get to a height of h sub f? Well, the person is going to apply a work to it, right? The person is going to apply work to this. So they're going to be pushing this object up. What that means is, essentially, they're going to be injecting an outside force, a non-conservative force. These last two guys are the non-conservative forces into the system, right? And that's what this is right here. And then it's going to then get to a height of u sub gf, right? So I gave it 3 blocks of injected work. So 1 plus 3 is going to be equal to 4, and now it's got 4 blocks of energy, right? And I should adjust the size of my pie chart to coincide with that, right? So this is 1/3 and this is 2/3, right? Actually, this is 1/4 and this is 3/4, right? And now it's all 100%. So you have to think about, where is that work coming from, right? Well, what is happening to get it to this height U sub GF? Well, work is being done initially to push it up to that height, right? So the total energy has to be where it is, a height up, plus, its initial potential energy, plus work that you're injecting into that system from outside. And that's how you get this. Okay? So what I want you to do now is correct your pie charts and bar charts. And I want you to then convert this stuff using these equations that we've written to equation form. Okay? So there we go. Go ahead and pause the video and try that out. So let's go ahead and try it. I'm going to go ahead and type that in, since that's what you have to do to fill out these guys. So we have initial energy. You always start the equation stuff equal to the final energy, right? And I'm looking at both the bar charts and the pie charts, whichever one you like more. So the initial potential energy plus the work is this initial bar chart and pie chart, and that's equal to the final potential energy. Okay? Initial potential energy is going to be mghi plus force times the displacement. In this case, the displacement is going to be hf, because you're going to lift it to hf, minus hi. And in the end, the potential energy is going to be mghf. Okay? So having that done, what we could do is we could actually go ahead and if we needed to, we could solve for any one of these variables, right? So we have mghi equal plus the force that the person is lifting with, which is the weight of the object, is the weight of the object. I should also note that it's the mass of the object, times delta H equals mghf, right? And the mass is, we're doing a force diagram on the ball, but the person's got to lift up that ball, right? And the ball weighs mg, right? mghi, and this is going to be equal to mghf minus mghi, and that's going to be equal to mghf. So what you would have to do is bring mghf onto the other side with this guy. And so let's go ahead and try that. Okay, so this is going to be equal to mghf. So it's mghi, just brought that down here. I'm going to multiply mg by hf, and then mg, that shouldn't be there, times negative hi. So this is mghf minus mghi equals mghf. Something really cool happens, right? Notice we're going to have to bring this onto the other side. And when we do that, what you see here is that this mghi is going to be subtracted off by this mghi. And that's equal to mghf minus this guy, because we have to bring it on to the other side. And so what you find out is that this is actually works out to be 0 is equal to 0, which is crazy. This is an interesting problem because of one thing that we had to consider. If you're moving something at a constant velocity in between here and here, meaning you're not accelerating it up, and it all hinges upon this, right? If the force that you're applying to something, and I'll do a force diagram on this, right? You got the ball. Oh, excuse me. Got the ball. You're pushing it up, and as long as you're pushing it at a constant velocity, right, the acceleration is going to be 0, right? And so what that means is if you were accelerating it up, this force would be greater than mg. It would be equal to mg plus mass times acceleration, right? Because we did that problem in force diagrams, right? But since this force is, since we're traveling at a constant velocity, the acceleration is 0. So even though it's moving upwards, there's no acceleration. So that means when we sum the forces in the y direction, force up minus mg down equals mass times acceleration in the y direction, but that is 0. So the force is equal to mg. And that's why I wrote that force is equal to mg. If it were accelerating up, then this would be force equal to mg plus ma. But we're not. So why does this become 0? Well, if you're moving it at a constant velocity like you're doing here, okay, delta k, which is the k final minus k initial. Well, if it's moving at a constant velocity, the initial velocity is equal, well, constant speed, I should say, the initial speed is equal to the final speed, which means this is equal to 0. And since delta k is equal to work, right? What that means is that you are doing 0 work, right? So even though you're lifting this thing to a height, right? The fact that you're lifting it at a constant velocity is why this thing works out to be 0. So that's one of the weird little things about how energy can work, right? So cool problem. I like doing stuff where the solution, well, the answer is very confusing, and then I have to kind of think about it, right? And it was all loaded in this constant velocity thing that is in the stem. So that's an interesting problem related to work. Well, we talked about, and this is another non-conservative force, and by the way, in the what I love about the energy bar charts is it accounts for non-conservative work entering the system or leaving the system. That work could be a force or it could be friction, right? But with friction, what I like to do is keep it in the system and then account for it using thermal, E-thermal, okay? So here's what's interesting about friction. So friction can, in almost all cases, friction can take away energy from a system, right? Friction will convert kinetic energy, it will do negative work, right? And then when it does that negative work, basically, since work is equal to delta K, again, to remind you guys, so K final minus K initial is equal to work, right? And so if the final, so if you're slowing something down, this initial, this guy is going to be small, and this guy, so it's going to be moving really fast in the beginning, and then it's going to slow to a stop, right? And so that results in a negative K, a negative delta K. And so that's how energy is going to be negative work, right? If it speeds it up, it'll be positive, right? So that means if you start out at 0 and you have a final kinetic energy that's higher than the initial one, that means this is going to end up being positive work, and there you go. But suffice it to say, most of the times, if an object is moving to the right, the friction vector, and specifically the kinetic friction vector, if that's to the left, that is going to be doing negative work, right? Negative work really is if the displacement of the object is to the right, and I should actually make this a displacement vector, right? It's horrible. I'll go ahead and erase this, and I want to make that a displacement vector. So this will be a displacement vector. If the object is moving to the right, meaning its velocity vector is to the right, but the friction vector is opposing it, that means it's doing negative work. And if friction is doing negative work, it's taking that kinetic energy and converting it into heat. So depending on your perspective, you could say that that is taking energy out of the system, right? So since we are calling frictional energy as thermal energy, we're going to try to keep it in the system and count for it, right? But friction is considered a non-conservative work, which means it can add to the system or take away from the system. It could add energy to the system and take away energy from the system. And so we're kind of talking about a moment so friction, we talked about kinetic friction and how most of the time if an object is moving to the right, it's working against it, right? Well, how can it be that friction can add energy to a system, right? Well, how do car tires work? How do your feet work when you're moving, when you're running or just walking on the ground, right? Well, that's a static friction. And I'm not trying to say that static friction is going to always add energy to a system or whatever. But what I'm saying is this, static friction can add, basically, friction can also add to a system, right? So if you have a box in the back of a truck and that truck is originally not moving. So we have a box sitting in the back of the truck, right? Well, if the truck starts to move, right? Let's say this. I'm going to need a little bit more room to do this. If we have a block sitting in a truck, it's got a normal force up, it's got a weight vector down, right? And if it starts to move to the right, and let's actually say this, it's actually speeding up as it's moving to the right. Speeding up means the velocity vectors and acceleration vectors in the same direction. Well, what that means is, that means that here's the bed of the rock, it must be rough, right? And that means the friction vector, the static friction vector, if it's not sliding, is actually pushing it to the right. And that is the static friction vector, right? So the static friction vector is going to be what is pushing it to the right as it's being displaced to the right, okay? So in this case, since the displacement vector and also the velocity vector are in the same direction as the frictional force, it's actually adding energy to the system, right? It's now a positive work, which could be said that it is now adding energy to the system, right? So it's doing positive work. So that's how friction can add or subtract energy from a system, right? In this case, you have a block being sliding across the ground, right? So it's moving to the right up here. This block is moving to the right, and it looks like she's pushing it slowly. So that means the displacement vector will be to the right in the same direction as the velocity vector. But the friction vector, which is kinetic friction in this case, is working against it. So this is negative work. And since work is, in most cases, an external energy, it's actually taking energy, it's taking that kinetic energy out of the system, right? But since we're talking about frictional energy, we're going to keep it in the system. Okay, we'll talk about that later. But I'll leave that alone for now, okay? Well, let's go ahead and move on, and let's work with this, okay? Again, just to remind you, mu sub s and mu sub k are the frictional coefficients. They don't have any numbers associated with it. That's it. So work is going to be equal to the frictional force, which is mu sub k or mu sub s, times the normal force. So that's the frictional force times the displacement. Basically the path that the object is in contact in the ground while the object, while the rough ground is working on it. Okay? So let's move on and let's try an example. Here we go. We have a box of mass M sliding across a frictionless surface right over here. Okay? So it's moving here. And it looks like it's moving really fast. That's why there are two greater than signs. It hits a patch of rough ground. Okay, and that rough ground goes over a distance d. Okay, and then it still is moving here. It then hits another patch after it crosses over that to a patch of smooth part, which is, it now is still moving, but it's just not moving as fast. So what you're supposed to do is what I want you to do is, given that as your prompt, go ahead and do a pie chart and do the pie charts and bar charts for this case. In this case, I would also like you to keep that this frictional force work is a thermal work, and he has it noted right there and right there. We're going to try to keep this in the system. Okay? So go ahead and try it out, and let's see what you get. Go ahead and pause the video and try those. Okay. Let's keep moving. So here we go. This object initially is moving right over here. And it's moving with a kinetic energy, K initial, right? It's not falling to the ground, so it has no height off the ground. There's no springs attached to it. So there's nothing really, there's no other energy other than kinetic energy. So let's give this, I don't know, let's give it 3. What do you think? 3? Let's give it the full bar chart of energy. Now, let's talk about over here. Let's talk about it over here. Now, what are we doing here? Well, it goes through a rough patch, and that rough patch is what causes it to slow down. So that means that rough patch, and let me do this. Let's do this. It's still moving, and it's still moving a little bit quicker, but it's still got this chunk of energy that's missing, right? So it's moved through this rough patch, and that rough patch has eaten up a slice, and want to be consistent. I'm going to say this. It's eaten up a quarter of its energy. And that's subjective, right? I don't know. I'm just kind of making this up. And so what we're going to say is that energy, that friction, has been converted to heat. And now the object is actually hot. It's just kind of glowing. And so what you could say this is that if we had 4 little chunks of energy in the beginning, in the end, now we only have 3 chunks, right? 3/4, and that 1/4 of that energy is now due to heat. Okay, there is an alternative to this, which we could get into later, but since we have the option in these bar charts to keep this in the system, to keep that frictional energy in the system, I want you to do it. The one alternative is to say this. You've got kinetic energy, right? What you would have to say is that a chunk of that kinetic energy is leaving the system, right? A small chunk of that is leaving the system. So that is the negative energy. And in this case, we would call this the frictional force, right? And then we have 3/4 of that energy left over. And what that would result, what this would look like with an equation is that we have an initial kinetic energy that is 3 bars positive, but we have friction being taken out of the system. So this chunk is gone forever. This is actually only a partial pie chart, right? It's now lost forever. And that is going to be equal to the final kinetic energy. Had we left it in the system, right? Had we left it in the system, and let me do some erasing here. Well, actually, before I do this, if we continue on with our equation right here. I bring this work due to friction onto the other side. You get Kf plus W sub due to friction, right? Had we gone with our initial pie chart, you would still have 3/4 here, right? And then you would have 1/4 energy being lost here due to thermal energy. And then you would end up with initial kinetic energy is equal to final kinetic energy plus this thermal energy. So you end up getting the same thing, okay? So it's up to you if you want to take energy out and think about it at friction as negative energy, or keep it in the system as internal energy. And that is more of a personal thing that you have to decide on your own, okay? But I like to just keep energy in the system as an internal heating system, right? And not have it actually leave the entire system. These works are being injected in the system or taken out of the system, right? Either way, the mathematics works out the same. You get 1/2 mvi squared equals 1/2 mvf squared. And that internal energy right here, again, is just friction energy, which is going to be mu sub k. Since it was sliding and moving, it's going to be mu sub k times the normal force. And this box is not moving up or down, so the normal force is going to be equal to mg in this case. The acceleration is 0 in the y direction, right? So that normal force is going to be mg, which we'll worry about later, and is times the distance, or the displacement distance, right? If this is di, this will be df, and so that's the displacement, right? And so that's a frictional problem, okay? Again, it's up to you, really. Do you want to consider negative energy and have that friction being taken out of the system, or just keep it in the system? Personally, I think it's a little bit more clear to keep it in the system here as internal energy, right? But it is eating up that kinetic energy, which is why you would consider it being taken out of the system. All right, let's move on. Let's do another problem, and we have a box in the back of a truck. So I talked about this in another slide, but let's do it here. We have a box in the back of a truck, okay? It's initially at rest. The truck is at rest, it's initially at rest. And then the truck starts to speed up while the box is staying in the back of the truck due to static friction. So the box is not moving relative to the truck, but since the truck is now moving, the box is now moving. So I left a space here for you to actually try to draw this. So that's what we're going to do. Let's go ahead and draw this, and we'll go ahead and draw the initial energy for the box not moving in the back of the truck, and we'll draw the final energy. So go ahead and make a little drawing here, and pause the video and try to account for this, okay? All right, let's go ahead and start. So I'm going to draw basically a horrible looking little truck, and it's like a, oh, this is just terrible. Oh boy. So that's the truck, but we're worried about the box. So the box is just sitting in the back of the truck is at a stoplight and not moving. So the box is not moving, and let's just say it's not going to slide off onto the ground, so we don't have to consider the height that it's at or anything. So basically, this is it. It's not moving. Okay? And since it's not moving, static friction is not really working on it right now. It's just sitting at rest. It's only when something has a force applied to it that static friction will start to work. Right? The friction forces will start to work. Well, now, that same picture, so I'm going to try to redraw it where the box is now moving to the right in the back of that truck. This is not a very good I'm going to draw those tires too. So now it's moving to the right, okay? Just to be clear, once it is moving to the right, it's got a normal force, it's got a weight of the object, and it's probably also speeding up as it's moving to the right. So that means the static friction force, which is mu sub A times the normal force, is to the right, right? So that's what is accelerating to the right. That's what's pushing the box to the right, is that it's connected to the truck by static friction, not sliding back or forth in the truck. Okay? So go ahead and pause the video and do your energies, energy final and energy initial, and let's see what you get. Okay? All right. Here we go. So there's a couple ways to do this. But we had talked about how work due to friction is equal to a thermal energy, right? So once this box just starts to get moving, well, now this force, this frictional force, is going to start working on it, right? And it's going to continue working on it way over here too as well. So there's a couple ways you could do this. You could actually say this: there is no energy in the beginning, right? But now, in the end, what happens is energy, or a frictional force, work due to friction, is being injected, which is resulting in a kinetic energy, right? And if you say it that way, what you're saying is this. Let's just say that 3 blocks of an outside energy is getting added to the system. This arrow means work energy is being taken out of the system, right? Which is not happening in our case. So I'm going to take that away. This arrow is energy being injected in the system, right? Well, that is going to then result in the object moving with 3 blocks of energy, right? And so what that's saying is that frictional force is driving this to the left and is giving it a final kinetic energy, right? So another way of approaching it is saying this, is that it's got an internal energy here, And you would say, in this case, it has an internal energy here, and that this block here, this stuff, all of that stuff is now gone. Okay. And so that's the internal energy equal to the kinetic energy, right? So there's a couple ways to do this, depending on what you like, but both of them result in the same thing, and that's mu sub s times the normal force, and since it's not moving up or down, that normal force is going to be equal to mg, and times the displacement of the object, right? The object is going to be moving to the right, and we'll say it's being displaced a distance, actually call it a distance x, a distance delta x, right? And that's equal to 1/2 mv final squared. So either of these things is completely valid. Okay, if you want to consider that it's just an internal energy, right? That ends up becoming kinetic energy, right? Or do you want to consider that it's actually nothing in the beginning, no energy, and that this non-conservative work is being added to the system, that work due to friction is being added to the system, the initial system, and resulting in energy in the end. It's really up to you what your approach is. So I'm giving you two options to keep energy in the system, to let energy that work due to friction stay in the system as initial thermal energy right here, or to consider it as a non-conservative work and added to the system from outside. And that's what this part is being added to the system or taken away. It's up to you. So let's talk about springs. That is the other type of stored energy that we're talking about. And we also did a little bit of, I showed you how we got this as being 1/2 kx squared, right? It's the U sub s is spring energy. I'm going to change that. That should say U sub s. Anyways, which is equal to the spring force dx. We're going to integrate it from the initial to the final, right? And what you find out that is 1/2 k, and that x is being squared, so it's you integrate that's x squared times 1/2, and then you have to put in your limits, and you end up getting this. And so this is the spring constant, right? Which is newtons per meter. It's how stiff, or it's the stiffness of the spring, how much it's going to really fight you, right? And delta x is displacement distance, and what that means is past the equilibrium position, right? So all springs want to snap or snap back to its original equilibrium position where it's relaxed. So it's going to, a compressed spring will push, a stretched spring will pull. And again, a Newton meter, it's going to be in joules, and this is a potential energy or stored energy. Okay, well, let's try a problem. You have a ball sitting on a spring, right? And it gets compressed a distance x, okay? But the ball on this compressed spring is a height off the ground, and it's being held in place and it's not moving, okay? It's now shot up into the air, and now the ball gets to its highest height, its maximum height, h sub f, right? And at this point, if a ball gets shot into the air and it reaches its maximum height, is it moving at that height? What do you think the final velocity is going to be? well, it's going to be 0, right? If it gets shot up and has gone as high as it's going to possibly go, all that kinetic energy has been turned to potential energy due to gravity, right? The Earth is what brought it to a stop. So the Earth is now, your kinetic energy is added to the Earth's energy, and now that is potential energy due to gravity. Okay, and it's at a height h sub f, right there. So what I want you to do is take a moment and go ahead and put this into pie chart form, okay? And bar chart form, sorry. So go ahead and try it. Okay, well, here we go. So this ball is on a spring and it's being compressed. And it's a height above the ground. So we're going to say this, that I want to be clear. I'm going to say this, that its potential energy due to gravity is really low, right? And that spring is a really stiff spring, so it's actually really coiled, and most of the energy there at that moment is U due to the spring. Okay? Well, now it gets shot up into the air, and it's been slowing down as it got to the height up there, and then at that instant it's at its maximum height. So it's been converted all to potential energy at some higher height. Okay? So here's what I'm going to do. And again, this mix of energy is superficial. Not superficial, it's subjective. So I said that is 1/4 energy there. I gave it one little block of potential energy due to gravity there. And I'm giving it 3/4 of that total energy of that pie chart is this. Okay? And so since the final pie chart is then is now completely just all potential energy to gravity, this is what we get. All right. So take a moment and convert this initial energy and this final energy to the energy form. Okay, so take a moment and go ahead and do that. All right, let me go ahead and I'm going to go ahead and mark this up. So the initial energy here is equal to the final energy over here. Okay, so that is the initial energy, and this is the initial, this is the spring's potential energy, and in the end it's potential energy due to gravity, final. So let's go ahead and then keep putting in our equation. So it's mghi, and this is going to be 1/2 k, and it got compressed a distance x from the equilibrium position. So that's 1/2 kx squared. And in the end, it's going to be mgh final. So it's gone to some maximum height. All right. This spring problem, relatively easy, pretty straightforward. It's when you have to deal with work and friction that it gets a little weird. You have to think about injecting energy into the system, right? Let me go back to this one right here. We injected energy into the system due to the initial system, and that's how it got to its highest height. That's how it got up there. And friction can be either considered as a part of the system as internal energy heating it up, or you could have this guy actually be a negative energy being taken out of the system. So that's really up to you. But when it gets to those non-conservative works, F delta X and the frictional force delta D, of course, so mu sub k times normal force times the displacement. You have to think about energy being taken out or in if you want to keep it as this, okay? if you want to keep it, if you want to inject it into the system or take it out of the system. Okay? So cool. What I want you to do now is I want to talk to you about power. Okay? So the last thing that we have to talk about. Power is, you've probably heard the term watts, right? If you've looked at a light bulb, well, an old light bulb, they would have 60-watt light bulbs and that, right? And so now new light bulbs, the diode light bulbs, for example, they are only using something like 5 watts, right? So 5 watts of energy as opposed to the old light bulbs is 60 watts. So what's really cool about power is it actually has 2 elements to it. It actually is the energy, right? The total energy of the system divided by time, right? Or it's the amount of energy being lost, so that non-conservative work from the system over time, right? And if you are a kinesiologist, or you are an exercise physiologist major, and this is also known as intensity, right? So power is equal to intensity. If you're talking about exercise physiology, right? So you can't really say that power is work, right? Power is how much work is being done over some time period. Or what you could also say is how power is the amount of energy lost over time, if you're talking about light bulbs, right? If you're talking about people exercising, that would be you would consider this is the person, how much work they're actually doing. It'd be like lifting a weight or jumping, right? It would be, if I jumped, it would be how many jumps, or what is my total potential energy change over time, right? So this is the work being taken out of the system, or this is the total difference in works. It's delta E, right? So that's the work being taken out of the system, or the work being injected in the system. It's the non-conservative work, right? Over a time period. So a watt is a joule per second, right? And so some examples that we were just talking about is a worker is using power to run upstairs. A worker might actually use more power if they run upstairs, right? So if you think about it, if you run upstairs, and let's say you run up 500 flights of stairs in, not 500 stairs. So let's say you run upstairs and you run up 50 feet, right? And it takes you, if you've ever done stadium runs, you're kind of running up the side of those stairs, right? You would actually be doing more power, right? Or doing more wattage than a rock climber climbing straight up the other side of that stadium 50 feet, right? A rock climber is going to take a slow, long time to climb straight up. And so it's weird. They don't have a lot of power in their system. So we have almost this weird misconception that we associate power with the amount of work done. That is not true. It's the amount of work done over a time interval, right? And so that's why you have Olympic lifters that are considered, when they do training, that sometimes they call that power training, right? If they do strength training. And so they're moving a lot of weight sometimes in a flash of an eye. If you've ever seen a jerk or a clean, in Olympic lifting, those people sometimes move so fast, you blink and they've actually already got the weight up in the air, right? So they're both strong, but they have a lot of power. And so that's kind of what training for fast twitch muscles is. It's called power training, right? And it's moving weight very quickly, right? While strength training, what bodybuilders do is they try to move weight very slowly and consistently. So they're going to be moving a lot of weight very slowly, which is the counter to this. It's actually the opposite type of training that you'd want to do if you are doing training to be Olympic lifter. Okay, so there's two types of powers that you have to deal with. It's two types of trainings that you have to deal with when you're doing that kind of stuff. And power, again, is the amount of work done over a time interval. Okay. The one last thing I want to talk about is efficiency, right? So efficiency is, so if you're ever dealing with the engine, it's efficiency is the percent. I'm going to draw a little percent symbol. It's the amount of energy output. Actually, I'm going to not put that right there. It's actually, well, if you take the total energy that you've put into a system and take the total energy that is being output to the system that is useful to the system, so that if you're talking about a car, this would be the total kinetic energy driving the car forward, and this would be the fuel consumed, right? And so that's the kinetic energy is the useful part of the output, while the fuel consumed is the total energy being put into the system. So this is going to work out to be a percentile. And in most, I think in the best of cases, you're talking about maybe a 30% efficiency. And that's like with really good type of cycles. There's the diesel cycle, for example, is a very efficient use of energy, right? I think most cars work on the Otto cycle, OTTO, not AUTO, OTTO, right? And diesel fuel systems work with on the diesel cycle. So that's why those big trucks, hauler trucks, use the diesel cycle. Okay. So let's talk about this question. A certain machine is 30% efficient. Okay. This means the machine will convert 30% of the energy input to useful work. 70% of that energy input will be wasted. 70% of that energy input is useful work. 30% of the input is wasted. Both of the above or none of the above. So from what you just learned about efficiency, what do you think the answer to this is? Well, let's go ahead and talk about it. Well, efficiency, again, is the amount of useful work divided by energy in. Okay, so initial energy, right? Energy put into the system, useful work. Well, basically what we're kind of doing is let's actually do this. Total change in energy. This is a work energy theorem, right? So this is E final minus E initial, right? And equals to the amount of work done, right? So in a way, what you could say is this is the useful work, right? Okay. And so the percent of useful work being done, okay, if that's 30% efficiency, what that's saying is that 70% of that energy is leaving the system, right? So this this is the energy lost due to friction, probably, right? And so this is the useful work, okay? And this energy leaving the system is actually due to that frictional energy, okay? So the answer is A, all right? What I want you to do is I want you to go ahead and move on into sapling and do your sapling homework or your mastering physics homework if you're in those classes, all right? So that concludes all of energy. Go ahead and start doing your other assignments and move through the modules. And I'll see you next time when we get to momentum. All right, have a nice day.